in this case, an intramolecular aldol condensation. If you can identify that you are doing an aldol condensation, but it's a little bit challenging, why don't we go back and review how do we learn the aldol in the first place, in the first time we were introduced to this reaction. And an aldol occurs when you have an aldehyde or ketone, and you have a base, typically an oxide base or a base that allows for equilibrium. And in this case, we're doing a self-aldol condensation. This is the first example that I show my students, and then we're going to try to apply it to this more challenging problem up here. Okay, but this one is a self-aldol condensation. And if you know this already, go ahead and test yourself and draw the product and possibly even the mechanism. But for this video, I want to try to figure out some shortcuts. What I typically do is I draw another molecule of itself, because in the self-aldol condensation, the enolate form is going to attack the non-enolate form. The enolate form will form will deprotonate at the alpha carbon, and it's up to the student whether you want to draw the O enolate or C enolate. We're not really worried about mechanisms in this video. We're worried about how to get the final product. And ultimately, the alpha carbon makes a connection to the dot right here. Okay? And what happens is you get an intermediate. So let me draw the intermediate in a different color. And I like to say you draw the attacker as is, but you could conform it so this other two carbons are out of the way, and then we attack the dot. Okay, so the alpha dot connection is the one being made, and ultimately for this intermediate, the double bond O that we see in the light blue drawing becomes OH. And just copy the rest of the molecule. Okay, there isn't a hydrogen here. Okay, there is a hydrogen also here. Right here. Okay, sorry, it's so tiny. And so this molecule has the opportunity to dehydrate by removing this H on the alpha and this OH on the dot. Ultimately, your final product, which I'll draw in blue, is this. Do you see how we still have the aldehyde attacker drawn identical to what it looks like in the starting material? And then we made a double bond because of the dehydration, and then we have these three more carbons. So you do double the number of carbons. We went from 4 to 8. You do have this alpha carbon, and you do have this dot. Okay, so can we apply that to this intramolecular aldol condensation? Look what we have to do. We have to make a double bond between the alpha and the dot. Okay, and the enolate that did the attacking kept its carbonyl group. Okay, and so when I take a look at this molecule, there are several alpha carbons we can use. We could use this one, alpha 1, alpha 2, alpha 3. There is no alpha 4 because that's not a carbon, not an alpha carbon. Now, if we look carefully, if I use alpha 1 and I do the same exact analysis, I'm going to be attacking this carbon right here. And the problem is that bond between that alpha and this dot is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. You will not make an 8-carbon ring very easily, so this will result in an 8-membered ring. I'm counting 1, 2, 3, 4, 5, 6, 7, 8. Okay. This alpha carbon, has no alpha hydrogens. Yikes. So here, there's no alpha hydrogen. So how can you make the enolate? You cannot. So our only option is A3 or alpha 3. Let me redraw this. Again, before I redraw this, what's the shortcuts, right? For the shortcut, you make a carbon-carbon double bond between the alpha, that was the attacker, and the dot. You know, that dot used to be the carbonyl carbon, okay? We ultimately get what's called a alpha, beta, unsaturated aldehyde or ketone, or just say unsaturated carbonyl. So if we don't get that in our more challenging problem, if we don't get this, then something went wrong. Okay. Again, I'm not going over the mechanism. I am just trying to find a shortcut to draw this product. Okay. So let's time this out. Here is your potential, this is starting material for your potential aldol condensation product. So knowing this, okay, you know this before going into the quiz or the exam. Let's apply that to this, okay? We assess the alphas, alpha 1, alpha 2, and we determined it would be alpha 3. With alpha 3, we are going to attack this carbon here, and we're going to put the dot. There is a double bond between the alpha 3 and the dot in the final product. We know that this ring, nothing happens to the original 6-membered ring. Here is the dot, right here. Remember what I said? We know there's a double bond between the alpha and the dot. We know that there's a bond, a new bond, between the dot and the alpha. So here's the alpha, okay? We know that there's going to be a double bond, and then we just have to fill in the rest. We have the alpha and we have the dot, and then we have them connected already. It goes alpha, 1, 2, 3, 4, dot. So that's 6, right? So it goes alpha, 1, 2, 3, 4, the dot. On atom 4, or alpha, 1, 2, 3, 4, on this 4, we have a methyl group. Alpha, 1, 2, 3, 4, we have a methyl group. And on alpha 3, let's call this alpha 3, we have not taken care of this group yet. It's not a carbonyl on the alpha, it's a carbonyl next to the alpha. It's a carbonyl next to the alpha, which is not part of the ring. That carbon is not part of the ring. And we have, oh boy, we have this. Now see, I made a mistake. I said alpha carbonyl, but not part of the ring. Right now, this is too far away and incorrect. We have this. There it is. And we have now this group. Ooh. So you see how easy it is to make a mistake? What you can do is visualize. This molecule was kind of curving around to get the alpha right here to make the double bond. When I do that, do you notice that this group is not part of the ring? It's hanging off the ring. But what you could also do is you can, let me show you this. You can copy this and redraw it and get rid of the bond that you think you made right there. Doesn't that molecule almost look like this molecule? We could double check. There are 4 CH2 groups. 4 CH2 groups. 1, 2, 3, 4. And then the carbonyl. True. originally we had a carbonyl right here. Okay, but you see, that was a connection that was made. Your final product was this, and you saw what was not the correct product, right? And let me draw it, because this is going to be also challenging for the graders, because there are a lot of similar looking molecules that are not the product. For instance, I was about to draw this. You know what prevented me from drawing this? I realized that from the alpha position, I realized that this is beta gamma. This is beta gamma unsaturated, not alpha beta unsaturated. Do you see the difference? So I knew that this ketone or this aldehyde was too far away. Okay, that is the challenging intramolecular aldol condensation. That is your answer. Okay, again, I know that you don't have time to do all of this on the exam, but this is stuff that you should know automatically before the exam. And then it is expected that students apply everything they know about this aldol condensation, what kind of molecule it makes, what is the key carbon-carbon bond connection, and then apply it to a system that is less simple. Okay. Let me take a look. Maybe, is there any others? At this point, I do have time. Let me compare this to the Claisen. Okay, and the Claisen that I have given before on a quiz is this one. I don't know if this is a good idea. Yeah, let's do it anyway. OET plus, because it uses the same concepts as the aldol, meaning that you'll make an enolate that attacks a non-enolate. In this case, our molecules are not aldehydes or ketones, they are esters. And there will be a profound difference in the final product because we're using esters instead of aldehydes and ketones. The profound difference is when you attack an ester, you will kick out its leaving group. Okay. Again, let us work via analogy. And before I do that, this is technically called a crossed Claisen because we're using two different molecules. It's not a self-Claisen and it's not an intramolecular Claisen. Okay, for the cross Claisen, again, I'm going back to aldol actually to see what we did. We formed the enolate by deprotecting the alpha and we attack this. Now, when I do the attack on an ester, there's actually going to be a leaving group. In this case, there is no leaving group, okay? But in this case, there is a leaving group, okay? Now, why did I choose this one to be attacked and this one to be the attacker? Because the molecule on the left is the only one with alpha hydrogens to remove. And we could form the enolate on this molecule, but definitely not on this molecule. There is no alpha carbon on this molecule here. Okay, and so, again, we're going to do the shortcut. We're going to go ahead and we mark the alpha ready, and we're going to attack guess what? We're going to attack the dot. But now, instead of doing all of this stuff, where we make the OH and we get rid of it, instead, what happens in the mechanism is we make the O minus, one of the lone pairs comes back down, and we kick this out. So I'm going to remind myself, kick it out. Leave. This is the leaving group. And that's it. Draw. I'll do it up here also. Draw the attacker as is. Okay, that's horrific. Bond angles are not great, but as is. So the attacker doesn't lose its leaving group. Now here's the tricky part. And a lot of students do have a problem with this. Not that the molecule is too big. Students have a problem when the molecules are too small, and you don't see like a carbon flag or any, a long chain carbon chain to kind of mark, where everything is, because it's going to look a little strange. You attack the dot, and there's really nothing else on it, literally, right? Because we kicked out the leaving group, we just have this carbonyl, and we still have this H right here. So students kind of freak out when they see something like this. They follow the directions, or they follow their notes very carefully, and they kind of have doubts about, is that really correct? You shouldn't have any doubts if you made a beta keto ester, right? Because look at the alpha, and I'm using the ester as the starting point. From the ester, I make it alpha, and here's the beta carbon. So your beta is right here. There's a keto group, right? There's a keto group on the beta position. So the keto group is an acyl group, or a carbon double bond oxygen, and it's the beta position of the ester. That is your cross-Claisen right there. Let me see if there's any other ones I want to go over. So when you're having aldols and Claisens, right, you have, give me a second, you have aldol and you have Claisens. I tell my students to go ahead, if you can, if it's a possibility, don't just stop at the aldol product, the one with the OH. See the orange? Go on to the blue. Right. Don't stop here. If you're able to do a dehydration by removing H and OH, go ahead and do that. Okay, and it has to be conjugated. Okay, don't make a double bond like over here on the other side, or over here. Okay, so we call that condensation, when you make the double bond between the two carbons. So you'll have either aldol or Claisen, and either one of those could be a self reaction, a cross Claisen or cross aldol, or we started out with the intramolecular. And yeah, we did an intramolecular aldol condensation, but you could also have an intramolecular Claisen. Technically, it's called a Claisen condensation because the leaving group, in this case, OET, becomes HOET, and it starts to condense. You'll literally see droplets of liquid. All right. Is there anything else I want to do? Let me do two more. Okay, let's test ourselves. Are these going to be aldols condensations or Claisen condensations? You decide. And you decide also whether it's going to be self, crossed, or intramolecular. Interesting. For this one, I would probably specify that we have a 1-to-1 ratio, so equal molar of these two reactants. Just to give away the twist, if it wasn't 1-to-1 and it was 2-to-1, you have two alpha positions here, and you could actually have a condensation on this side and also on this side. But here I'm saying it's 1-to-1, only combine one of these with one of these. And the last one I want to give you is this one here. Okay. Interesting leaving group of the ester. Interesting base that we have to use. For the R groups for each of those has to match the R group of the leaving group. I won't go into that right now. Maybe in a separate video I will. Okay? Pause the video, because when I come back, I'm going to do this pretty fast without much talking. All right, good luck studying, and don't forget, you were taught these rations with simpler versions first, and see if you can apply those to the more challenging problems that you'll see.